try to present you the basic a priori estimate that we can use to construct a possible limit and a solution of our gradient flow, and let's say a fundamental interpretation of the solution of our variational problem. So let me start recalling you what we are doing. I will not repeat the usual assumption on the space and on the functional, but we are minimizing the functional defined on trajectories, which is just the integral from 0 to plus infinity of epsilon over 2 u dot square plus phi of u of t, integrated with respect to the usual measure mu epsilon of t among all the possible trajectories which are in AC2 log of 0 plus infinity with values in x with given initial condition u bar. Okay? And we have seen that whenever there exists at least one curve with finite I epsilon of u, then a minimizer exists. So there exists if, say, u bar is in the domain of phi, then there exists u epsilon, a minimizer of I epsilon of u. Okay? And we want now to study what are the basic property of u epsilon. Let's say that we have just, in this general setting, we have just one estimate, which follows by a standard idea here, which is called the inner variation of the function. So I write it here, inner variation estimate. It tells you that if u epsilon is a minimizer, then the map from t to phi of u epsilon of t minus epsilon over 2 u dot epsilon square, this map, which is in L1 lock or in L1 with respect to this measure. This is also a Sobolev function, so is W11 lock. This is a real function of the interval 0 plus infinity. So as an extra regularity. And if we calculate its distributional derivative, so the distributional derivative of phi of u epsilon minus epsilon over 2, the metric derivative square. So in principle, this is just L1 lock, but it has a distributional derivative, and the distributional derivative plus u dot square is equal to 0. So the distributional derivative is the opposite of the metric velocity. Okay. I'm not saying at this level that this is absolutely continuous, since I have a priori no regularity on phi. It's just lower semi-continuous along the trajectory. This is just an L1 function, so I cannot use here AC, but just the Sobolev space. Okay? Before showing this, is a very simple argument. Let me give you why we can expect this estimate in the smooth situation. So in the smooth case, we already derived the Euler equation. Smooth case means that phi is C1 and X is an Euclidean space, okay? Of course, also more generally in Hilbert, but just to see the idea. The Euler equation is minus u epsilon u dot dot plus u prime plus the gradient of phi of u is 0. And we have just to multiply this Euler equation, multiply by u dot. And what you get is minus epsilon. So u second multiplied by u prime is just the derivative, the time derivative of u prime of t square. Then you have u prime of t modulus square, and then you have the gradient with the derivative is just the time derivative of phi of u of t equals 0. Okay? So you see that this is very obvious at the continuous level, and one of the advantages of this inner variation estimate is that I should say equation, but of course it provides an estimate, as we will see in a moment, is that is purely metric. So here we need vectors, but now here we have just derivative of scalar quantities. Of course, it contains very few information with respect to the Euler equation. In the Euler equation, we take arbitrary variation. In the inner variation, we will see that we take variation only with respect to time in the your interval. But still, it is interesting, since at least written in this form, if we are able to neglect this negative contribution, in the limit you formally have the energy identity that the time derivative of phi is minus the velocity square. So this is what we will need at the end. I cannot, of course, in the distributional sense, I can split the derivative there, but if I want real Sobolev function, is only the difference, which is a Sobolev function. You are not allowed to say that phi of u epsilon is Sobolev and the metric derivative is Sobolev. It's only the difference. Okay. How can we prove this in the metric setting? The basic idea is to take an inner variation. An inner variation means that in the integral we want to change, to make variation with respect to the formation of the time scale. So the idea is that you take a smooth family of, take a small parameter tau, small parameter, and take a smooth family I will call R tau of t, is a smooth family of diffeomorphism of 0 plus infinity. For instance, take just R tau of t is just t plus tau, a vector field, psi, vector field is a scalar function in this case, psi of t with psi c infinity with compact support in 0 plus infinity. Okay? For small values of tau, this is an invertible function. And this is typical, and then you just, you may invert it, and you define a family of competitors for your functional, which I will call u tau, u tau of a new variable s is just I will put a tilde here to distinguish that tau here is not absolutely not related to the parameter epsilon. So u epsilon is the minimizer, and you take just r tau minus 1 of s. So the idea is that t is just r tau of s. R tau minus 1 of s. Okay, and so you put inside this, you put this function inside your integral, and you get that I epsilon of u tilde tau. If you write and change the variables, you will see that this is the integral. So you just substitute everything, and then you make a change of variables by putting s equal r tau of t. So you get here e minus r tau of t divided by epsilon. I need to write explicitly the measure. And then you have epsilon over 2, the minimizer square, divided by r prime tau of t, plus r tau of t prime phi of u epsilon of t, everything integrated with respect to t. I skipped one step of the calculation, but it's quite simple to check it. So the advantage of this inner variation is that when you compute the functional along this new curve, you may rewrite the integral in terms of the old minimizer, but with this extra term perturbing just time. And they are not inside phi and inside the metric velocity, which are no smooth object. They are just parameter inside the integral. And then you can just differentiate this function in tau equals 0. So by the minimizer property, you get that the tau derivative of the functional at tau equals 0, this tau derivative should be 0. This is a smooth functional which has a minimum exactly at tau equals 0. At tau equals 0, notice, sorry, I forgot to mention here that at tau equals 0 you get the identity. R0 of t is just t. And so everything here disappears, you get the function, the minimum of your integral. Okay, and if you compute this derivative, you have to do some calculations. And what you get at the end is this expression. You have first to differentiate of this quantity, so it is, and notice that when tau is 0, this remains just t over epsilon, so you have here e minus t divided by epsilon over epsilon, and inside the parentheses you have just minus epsilon over 2 u dot epsilon square, and the derivative with respect to tau, let me observe that here r prime tau of t is just 1 plus tau psi prime of t, and when I differentiate also with respect to tau, the tau derivative of this expression is just psi prime of t. Okay? So when I take the derivative of this quantity in the denominator and evaluate at tau equals 0, I have just minus psi prime of t here, and then I have psi prime of t phi of u epsilon, and then I have to differentiate this term, obtaining minus the derivative now of the tau derivative of r tau of t is just psi of t. So we have plus minus psi of t divided by epsilon that multiplies all this term. Epsilon over 2 u dot epsilon square plus phi of u epsilon. Okay? And dt. This is the computation. It's a little bit tedious, but nothing difficult. And then I hope to make everything correct. And then you just observe that here you have an integral from 0 to plus infinity. Here you have phi of u epsilon minus epsilon over 2 u dot epsilon square, which is multiplied by psi prime. And then you have also a contribution of phi here with a different sign. So I just put here minus psi divided by epsilon. And then there is an extra term, which is minus psi divided by epsilon, which multiplies this quantity. And it is just u dot epsilon square. Everything is integrated with respect to mu epsilon, and this 0. Okay. So there is a factor 2, but I put 1/2 here, and then I gain a factor 1. Okay, I skipped some intermediate passage, but I want to have this operator here, since by integration by parts with respect to this measure, this puts a derivative on this quantity. And you get exactly the integrating by parts. You have a distributional derivative here with the minus sign, minus u dot square, and so you get this quantity, this expression. This provides you that the first you have to observe that this quantity has a derivative in L1, and eventually you find that phi minus epsilon over 2 u dot square plus u dot square equals 0, since psi is arbitrary. Okay? This is the way you can derive the estimate. Okay. This is the first information, and then of course, we need some more insight in the equation, since, as I mentioned, this estimate is too weak to hope that it's sufficient to pass to the limit. And let's say that in the vectorial case, as Mielke-Stefanelli did, you can play a lot on the Euler equation to try to get extra information, but we don't have the Euler equation, so we need a different strategy. And the idea is to recall a nice interpretation of this minimization problem in the framework of optimal control. So the second step is interpret the WED WED problem as a very particular optimal control problem. And in order to see the analogy and what we can expect, let me still make the discussion at the level of the smooth situation, and then we come back to the metric setting. In which sense? You may argue in this way. Consider this situation that, of course, the basic point is that in all this minimization, we always consider the initial value as fixed, as a fixed given datum. Now the basic idea is to study the function that you obtain by allowing u bar to move, and to every u bar you consider the minimum value of this function. So the new object that enters in the game is the functional that I will call v epsilon of u bar. Then I will switch to the variable x in the next calculation. Is just the minimum of this quantity of I epsilon of u, minimum among all the curves, admissible curves in AC2 lock, with u of 0 equal u bar. So if you take this function, this defines a new function in the space x. So it's better to write here in order not to, since now we want to move this initial value, I will call it x. X is an element of your ambient space. When you introduce this function, you may interpret this as the value function of an optimal control problem. And in order to understand what we can expect by this interpretation, let me recall you the standard basic setting. So what we are doing here. The idea is that in optimal control you have a family of ODEs controlled by a parameter. So in our situation, this is the simplest possible situation where your control parameter is just the velocity of the curve, as is standard in calculus of variation. So we have just, I write the control in a very trivial form. V is just the velocity of the curve. Now I consider the smooth case. And the initial datum is u of 0 equal x. So given v and x, this defines a curve which is u of t, which depends on the initial point and your choice of velocity. And with this curve, you want to minimize the discounted cost, which is the integral from 0 to plus infinity, the exponential. Usually there is a coefficient in front of t. I will keep the t divided divided by epsilon. And then you have a Lagrangian, L, which depends on the position you are reaching along your curve, so u of t, x, and the control itself. And you integrate with respect to t. This is called infinite horizon problem. And you take the minimizer among all the possible control v. In this case, v is just an element in L2 lock of with values in your Euclidean space. Okay? This is the typical form that very simple, since in general, for general optimal control problem, you have here a true differential equation, so a function, f, another function, which depends on u and v. In our situation, this function is the simplest possible. Okay, and the Lagrangian for us is just the function that is 1/2 the velocity square plus 1 over epsilon phi of the position. Okay, so if you look in a standard book of optical control, you see that whenever you are in this situation, you have two important information about this functional, which I called v epsilon of the position, which is the value functional I've written there. Okay? You have, first of all, the dynamic programming principle. It tells you that v epsilon of x is the minimizer, can be written in this way, a very strange way, I will comment in a moment, still among all the possible controls, of what? Of an integral, but now up to a certain time, capital T, of the same expression. And then you end up with this arbitrary curve obtained by your control, and then you consider the final point of this along this curve, so at the time capital T. You calculate the value function itself, discounted by the factor, the exponential factor e minus capital T divided by epsilon. This is a simple but very useful formula, variational representation of your value function. I will justify in a moment this formula in our setting. And the second important property is that this value function satisfies an Hamilton-Jacobi equation. This Hamilton-Jacobi equation is simply this one. If you take v epsilon of x divided by epsilon, this epsilon comes from this coefficient, of course, plus the Hamiltonian associated to this system evaluated at x and at the gradient of v, this is 0. And what is this Hamiltonian? The Hamiltonian h of xp is just defined as the supremum with respect to all the possible velocity of minus p, scalar the velocity, minus the Lagrangian. Here I'm using the particular form of the control and of the E. Otherwise, the definition of the Hamiltonian is more complicated. And you recognize immediately that this is just the conjugate of the Lagrangian with respect to the second variable. This is the conjugate evaluated at P. Okay. In our situation, this is just, the dependence is just the square of the norm, so the conjugate is the square of the norm, and in this case it's just 1/2 modulus of P square minus phi of x divided by epsilon. Okay, this is in our situation. Moreover, there is a third important point that will explain the interest on this interpretation. And the third important point, which follows by combining the dynamic programming principle and the Hamilton-Jacobi equation, tells you that whenever you fix a point x and you want to find the best direction or velocity that maximize this right expression to give you the Hamiltonian, you have just to choose the velocity of the solution, of the optimal solution starting from x. So in practice, you have the optimal V, providing h of x gradient of v of x equal max, let me call v star, just to max equal minus gradient of v of x v star minus L of x v star. Okay, so the optimal v that you have to choose for a given fixed x to reach the Hamiltonian evaluated in the gradient of the value functional is exactly the initial velocity of the optimal curve. Okay, so it is exactly the u dot at time equals 0, so u dot epsilon at 0. And what is the interpretation? What is the optimal value here? The optimal value here is related to the derivative of the Hamiltonian with respect to P. So it means that this optimal velocity is just that the derivative, I write in this way, of the Hamiltonian with respect to the P variable in the, sorry, there is, no, minus here. Of course, at the end, the Hamiltonian is symmetric, so you don't care any difference, but this holds for arbitrary, even non-symmetric Hamiltonian or Lagrangian. So you have that V star is equal minus the differential of H with respect to P applied to the value functional. And since V star is just U prime, you see that your optimal solution satisfies the gradient flow equation, but with respect to the value functional. So at the end, you may reinterpret this third principle by saying that along your optimal solution, the derivative can be calculated by taking the differential with respect to P of the Hamiltonian. X is the initial value, so it is u of t, evaluated in minus the gradient of v of u of t. This is the equation. And in our situation, the gradient of the Hamiltonian with respect to P is just P. So you immediately see that in our case, you have just u dot of t equal minus the gradient of v in u of t, which is what really is important for us. Tells you that the minimizer is the gradient flow, but not of phi, of the value functional. Yeah? Yeah, with an epsilon. There is epsilon everywhere here. Okay? Okay. This is, of course, there is epsilon here, and epsilon here. Okay, and why is so interesting? First of all, from let's say philosophical point of view, we started by looking for the gradient flow of phi. Then we found an approximation by minimizing this functional. We still obtain a gradient flow, but not of phi, of the value functional. So we are still solving an approximate gradient flow. And now you understand why, even in a metric or general situation, you may opt to pass to the limit. What will be the strategy? Prove that V epsilon is converging to phi, and this is not difficult. And prove that you can pass to the limit in this equation. So the strategy now is, okay, we have an approximate equation, then hope that it is sufficient to pass to the limit in V epsilon, converge it to phi, to pass to the limit in U. This is the idea. So in some sense, this interpretation gives us a sort of information to interpret also the inner variation formula. Why? Since suppose that now we can prove more or less the same thing in the metric equation, how can we interpret here? Remember that, so interpretation. Remember that, as I mentioned, in this situation, u dot epsilon is equal minus the gradient of v. So whenever you have here this functional phi minus epsilon over 2 u dot square, we may hope that this is phi of u epsilon minus epsilon over 2, the gradient of v epsilon evaluated at u epsilon square. And if this is true, by using the Hamilton-Jacobi equation that I wrote here, and in this particular form, observing that this is, I have to write in here, the Hamilton-Jacobi equation is just V epsilon divided by epsilon plus 1/2 the gradient of V epsilon square equal phi divided by epsilon. So you see that the gradient of V epsilon square is just phi minus V epsilon. And so if the Hamilton-Jacobi equation is true, you get here phi of u epsilon minus the gradient square is just phi minus v epsilon, so this should be v epsilon. So this strange functional phi of u epsilon minus epsilon over 2 u dot square is a candidate that it coincides with the value functional. So you may reinterpret this equation as the time derivative of the value functional at u epsilon of t plus u dot epsilon square equals 0, which looks nice, is the energy identity of u epsilon that should be the gradient flow of the value function. But we can do another step by writing in this way and splitting this square as minus 1/2 u dot epsilon square minus 1/2 u dot epsilon square. It's funny, but it's useful. And then if we have this interpretation, so the fact that u epsilon is minus the gradient of v, you have here minus 1/2 u epsilon dot square minus 1/2 the gradient of v epsilon of u epsilon square. Okay, if we are able to prove something like that. And then if Hamilton-Jacobi holds, this is 1/2 u epsilon dot square plus phi minus v epsilon divided by epsilon u epsilon. So at the end, the inner variation equation should be written as in the correct form, in the form that d over dt, v epsilon along u epsilon t, plus equal minus 1/2 u dot square minus, there is a minus here and a minus here, minus phi minus v epsilon divided by epsilon evaluated in u epsilon of t. And is exactly the same inner variation, but now you have isolated a nice function that is decaying, and you have here the metric velocity, here a candidate to be the modulus of the gradient of v, so this is the Giorgi formulation, the Giorgi metric formulation of the gradient flow of v epsilon. Okay? It's not a proof, it's just a sort of indication of what you want to prove to conclude the argument. Okay? And this identity also provides you a natural candidate in order to pass to the limit, since you may integrate it. By integration from 0 to a final time, you get that v epsilon at the final time, arbitrary finite time, plus 1/2 the integral from 0 to t of u epsilon dot square plus phi minus v epsilon divided by epsilon at u epsilon of t in dt. This is equal to the epsilon of u bar, the initial value. I just integrated from 0 to capital T. And then you may hope that if you have this interpretation, then you can try to pass to the limit here, hoping that as epsilon goes to 0, this converges to phi of u bar. This should converge to phi of u epsilon of u of t. And then you have to pass to the limit here from 0 to capital T. This should converge to u dot square. And the crucial problem will be to pass to the limit and hoping that this will give you an upper gradient for the limit. Of course, if you have strong convergences, you can hope to preserve the equation, but what is interesting here is that it's sufficient to get inequality. And inequality is much easier to prove, since on the right-hand side, we will show it's easy to pass to the limit. On the left-hand side, just a lower semi-continuity is needed. So you have lower semi-continuity here, lower semi-continuity for free for the metric derivative, and what will be crucial is try to prove lower semi-continuity for this term. Okay, this is the strategy. Okay. Now, in what remains of this lecture, I will try to, guided by this finite dimensional structure, I will try to reproduce in some sense all these steps in the metric level by working at n. Of course, here in finite dimension you have gradients, you can do nice perturbation, but what is really interesting is that at least for the dynamic programming principle, this is quite robust notion, and is not difficult to settle also in the metric stuff. And whenever you have this, it always contains enough information at least to conclude that this basic equation holds without really using the Hamilton-Jacobi equation. Okay, so now I will study a little bit the value function, and I will prove the dynamic programming principle. Whenever you have this, we will find this formulation of the inner variation. Okay? If you have any question, yeah, yeah, yeah.
But then there, the epsilon minus the phi minus the epsilon over t converges to g squared.
Yeah, this is the. This is the delicate point, and what we are able to prove in general is that this is true for convex or lambda convex functional in metric spaces, and what we are able to prove is that if upper gradient, lower semi-continuous exists, then always the Lim-inf, the gamma Lim-inf of this functional, it provides an upper bound of an upper gradient. And so it's still enough to conclude the energy inequality. But this is really the difficult part. But this part is also difficult in all the other variational construction. For instance, if you use minimizing movements or other approximation, whenever you have to pass to the limit in the gradients, this is the difficult part. So you have to, in some situation it's easy, in other situation you have to work. And maybe in other situation it's not true, of course. Okay. So, I hope that at the by the way, I think that this value function has a nice, important property that could be better studied. We will need a few of them, but it can be, before entering in the detail of the proof, it can be interesting to compare formally this approach with the minimizing movement one. So in the minimizing movement, there is a similar value function that plays the same role. It is the Yoshida approximation, or Moreau-Yoshida approximation of phi. It's just defined by y t of phi, yt of x is just the infimum with respect to all the points in your space of 1 over 2t, the distance square of y from x plus phi of y. Okay? And we have seen now the value functional, the epsilon of x, is the infimum of this strange integral. Okay. In some sense, both provide a good approximation of phi, since yt is increasing to phi as t goes to 0, and we will see that the epsilon will increase to phi as epsilon goes to 0. And moreover, both of them satisfy a suitable Hamilton-Jacobi equation. For the Moreau-Yoshida approximation, you have an Hamilton-Jacobi of evolution, the time derivative of yt of x plus 1/2 the gradient of all the slope of yt square of x equals 0 under some assumption, with initial condition y of 0 of x equal phi of x. And as I want to show, this satisfies a sort of stationary Hamilton-Jacobi equation, which is v epsilon of x plus epsilon over 2 dv epsilon of x square equal phi of x. Which, by the way, is interesting, since if you try to solve the Hamilton-Jacobi equation by an iterative scheme, the resolvent associated to this equation is exactly, one step of the resolvent is exactly given by this equation. So these two equations are related, and in some sense, the value function of the WED approximation has strong relation with the Yoshida approximation, which enters in the minimizing movement method. So there is this hidden relation that is useful in some situation. So it's curious that in both the approaches, you end up with some Hamilton-Jacobi formulation, the equation. Okay? But this is just a remark. I will not use it. Okay. Let me show you just a few properties, and probably I will conclude everything tomorrow. So first of all, basic properties on V epsilon. One we almost already know, the functional V epsilon is lower semi-continuous. So this means that if xn is converging to x, then the epsilon of xn, the lim-inf of when n goes to infinity of the epsilon of xn is bigger than the epsilon of x. We can, why this is true? It's true since we are just this follows by the two steps we used yesterday to prove existence of the minimizers, by the lower semi-continuity of I epsilon of u, the integral functional. So the strategy is quite simple. If you start, you write v epsilon of xn is I epsilon of un, where un is the minimizer associated to xn. And assuming that everything here is bounded, you know that there exists a subsequence u and k, we proved yesterday, that converge pointwise to some limit u, pointwise. And u is a minimizer of the I epsilon with initial value x, the limit. And since I epsilon is lower semi-continuous, you get that the epsilon is lower semi-continuous. It's very simple. Okay. A second property is that the epsilon, if epsilon 1 is less than epsilon 2, then the epsilon 1 of x is bigger or equal the epsilon 2 of x. So there is a monotonicity, non-increasing monotonicity with respect to epsilon. And this follows by the formulation of I epsilon, this equivalent representation, that if we change variables, you can represent v epsilon of x as the minimum among all u in the usual AC2 lock with the initial datum equal to x, of what? The integral from 0 to plus infinity, and instead of integrating with respect to the exponential of minus t over epsilon, you just integrate with respect to minus t and change variables. And so you get here 1 over 2 epsilon u dot square plus phi of u of t in dt. This is just a rescaling. Maybe I could write w here. Okay, and you see that in this form, v epsilon of x is the minimizer, the minimum value of a family of functional which are non-increasing with respect to epsilon. Since when epsilon 1 is bigger, is less than epsilon 2, then here you have a higher coefficient. And so you have, by taking the minimizer, you have this relation. Notice that at this level, the optimal w epsilon of t, which minimizes this integral, is just related to the optimal minimizer of the usual formulation, but rescaled with a factor epsilon in front of t. So in some sense, if you look to this minimizer, you are just looking to the solution with a quick variable epsilon t. So the right scaling is the one I used, but for proving this monotonicity, this is also useful. Okay. And now let me state the most important, oh no, we have another, okay, the most important property, which is the dynamic programming principle. Which is nothing that which is based on this very simple idea. Suppose that you have fixed an initial point x and write your functional I epsilon of u starting on a path u up to, this is u, up to a final time, this is u capital T. So E epsilon of u is just as a first contribution, which is the integral from 0 to t of E minus t over epsilon, the usual expression. Okay. And then you have another expression, which is just the integral from, I write in this way, it should be the integral from t to plus infinity of the same quantity. But I change variable and I write everything from 0 to plus infinity. So I have to make this expression. Okay? And you recognize here that this is from 0 to plus infinity is exactly the functional I epsilon, but there is this factor here. So you put this factor outside of the integral. So you gain E minus capital T divided by epsilon, and you can remove it from here. Okay, and now you recognize immediately that if you want to, okay, this would be your path following u, but maybe you can have a better value of the functional if starting from u of t, you use the optimal path, which minimizes I epsilon, but with this new initial datum. So this quantity is of course, is better if you put this optimal path. So you construct an arbitrary value and then you use the optimal. So if you use the optimal, you can replace here this quantity as E minus t over epsilon, the value functional associated to u at capital T. Okay? Since, so you start from x, you follow any path, and then you decide to replace the path given by u by the optimal. You have this expression. This expression is still bigger than v epsilon. So at the end, you get that v epsilon of x is always less than the integral from 0 to capital T of E minus t over epsilon divided by epsilon over 2 u dot square plus phi of u in dt plus E minus t divided by epsilon, the epsilon of u of capital T. So whenever you choose arbitrary u in AC2 lock with u of 0 equal x, you have this inequality. Okay? But of course, if you choose exactly the best path starting from x, when you arrive here and you find the optimal path, you still find the same. So exactly for the optimal path, if u is now u epsilon, you get equality here. And so at the end, since you have always inequality and you have equality for the optimal, you have exactly the principle I stated before. So v epsilon of x equal the minimum of the same expression. Okay. And so this is the optimal, the dynamic programming principle. So it's very simple at the end. And now, starting from this simple principle, we can use it to get better properties on your functional v epsilon. The first property is that is a regularity. So regularity of v epsilon along AC curves with integrable phi. So the basic idea here is that we have shown before that v epsilon is lower semi-continuous. This is not so much, but if I test it along a better curve, so suppose that W is a AC2 lock defined in some interval AB with values in X, and you want to study the behavior of v epsilon along this curve. And we also assume that phi along W is in L1 lock of AB. So we are assuming some integrability of phi. So remember that v epsilon is well defined in the domain of phi. It could be defined also outside, but of course if you don't have any control of phi, it may happen that v epsilon behaves quite not so well. So this is a sort of mild control of phi along the curve. Then the curve v epsilon composed W of t is in AC lock of AB. And moreover, and you have this interesting formula. If you evaluate the derivative, which now exists since this functional is absolutely continuous, this is bounded by the metric derivative of W. And then here you are expecting the slope of V. And as for the slope of V, we can put exactly phi epsilon of W minus V epsilon of W divided by epsilon. So this play exactly, this provides you an upper gradient for V epsilon, but not along arbitrary curves, just along curves such that phi of W is in L1. Okay? I don't enter in all the detail of the proof, but I just want to show you that the dynamic programming principle easily provides you this AC lock, and then you have to work a little bit to get this estimate. But we don't really need it now. And the idea is very simple. In order to show that something is absolutely continuous, you have here your curve. This is W. Fix 2 points along your curve corresponding to S and T. And you want to estimate V epsilon of Ws minus V epsilon of Wt, for instance. And the idea is that, okay, you use the dynamic programming principle, choosing as an initial point x W of S, following this path for the time capital T equals T minus S, and then from here you replace it, you replace the path with the optimal path starting from Wt. Okay? So this difference is always bounded by the integral from, let's write in this way, from S to T. You have to make a change of variable, epsilon over 2 W dot of R square plus phi of W of R multiplied. I am using just the inequality in the dynamic programming principle, and here you have just E minus R minus S divided by epsilon in the R. And then what you have, sorry, I forgot here, E minus divided by epsilon. I minus T minus S divided by epsilon, V epsilon of W of T, and then I have to subtract W, the epsilon of W of T in this way, okay? And then this is, now you, since you are in a bounded interval, you just forget about this exponential. You just replace this by the positive part of phi, and you are controlled the difference between 2 points of the epsilon by an L1 function integrated from S to T, plus another quantity which is bounded, and this term divided by T minus S is also bounded. It's Lipschitz with respect to T and S. Then you switch the order, and you get a similar bound for the opposite difference, and then this provides you the AC lock estimate. Okay, it's just written here. So it's very simple. And I want just to conclude by showing what happens if you apply this estimate along the optimal curve, and then I stop. So as a particular example, you may choose W exactly equal to the minimizer of I epsilon with initial datum x, and you rewrite the dynamic programming principle not just from 0 to t, but from s to t. So you have that E minus s over epsilon, E of epsilon at u epsilon of s. So you choose the initial point 0, a point s, and a point t along the trajectory, plus the integral from s to t. So sorry, this is equal to the integral from s to t of epsilon over 2 u dot epsilon square plus phi of u epsilon e2 minus r over epsilon divided by epsilon in the r plus d epsilon at u epsilon t e minus t divided by epsilon. This is the dynamic programming principle applied to the particular curve u epsilon. Now you know that v epsilon along u epsilon is AC, and you also choose a point S, choose a S Lebesgue point for both the time derivative and for phi of u epsilon. And so you just take the difference and you get that v epsilon of u epsilon s e minus s over epsilon minus v epsilon u epsilon t dx of t over epsilon, you divide by t minus s. This is equal 1 over t minus s, this integral of the same thing. And now you pass to the limit as t goes to s. So here you have the derivative, pointwise derivative of the functional, which exists almost everywhere. And on the right-hand side, you apply Lebesgue theorem, and since you use s as a Lebesgue point, you can pass to the limit here. So at the end, you get that the time derivative of v epsilon u epsilon e minus t over epsilon at t equal s is equal to epsilon over 2 u dot epsilon square at s plus phi of u epsilon at s. And if you, multiply everything multiplied by e minus s over epsilon. And if you expand here, you get v prime of u epsilon at s. Let's say I write in this way, e minus s over epsilon minus 1 over epsilon, here I forgot epsilon, minus 1 over epsilon v of u epsilon s. Okay? Then you remove this quantity, and at the end you get that, I write here, the derivative d over dt of v of u epsilon at t equal s sorry, I made, when I calculate this expression here, I'm taking the opposite derivative, so there is a minus here. This is minus. So, and so this is the opposite, okay. So minus the derivative of this term, there is a plus here, I put on the right-hand side, is equal to phi of u epsilon s minus v epsilon of u epsilon s divided by epsilon. And then there is also the extra term here, which is 1/2 u dot epsilon square s. Okay, which is, I hope it is exactly the crucial identity I wanted to prove. Okay? And with this, I'm stopping here. Thank you very much. So I'm sorry since it's a little bit technical, but I hope that at least the connection with this dynamic programming principle has been clear, I hope. This is the crucial point to interpret everything.